All right, so today I'm going to talk about some joint work that I've done with Jason Breck, John Seifert, and Tom Reps on computing closed forms from numerical loops. So the problem we're interested in is loop summarization, the problem of, given a loop, computing a formula that's sort of a closed form representation for what that loop does at runtime. So for example, if we have the loop while I is less than n, I gets incremented by 2 and j by 1. I might summarize that by the formula: there exists some natural number k, representing the number of iterations of the loop, such that I prime is equal to I plus 2k, indicating the value of I after executing the loop is the value of I before the loop, plus 2 times the number of times I execute the loop. J prime is equal to j plus k, and so on. So once I have a summary, I can use it to answer questions about the behavior of my software. So for example, I might check whether my loop satisfies a partial correctness specification by conjoining the precondition to the summary along with the negation of the postcondition and asking a theorem prover whether this is satisfiable. So we know that checking validity of Hoare triples is undecidable in general, so we must give up on something somewhere. And the first place we're going to give up is that I'm not going to look at general loops, but I'm going to look at this very simple class of loops, which we call linear loops. So a linear loop is a non-deterministic loop where the states are just vectors of numbers, and the state evolves by applying a linear transformation. So x gets a times x. In the paper, we also go beyond this class to affine and certain classes of polynomial loops, but for this talk, I'm just going to concentrate on the linear case. So before I talk about how to summarize linear loops, I'd first like to motivate the problem a little bit. So yeah, why do we care about these simple loops? So the first answer is that it's a natural problem. Right? We're asking about the behavior of iterated linear maps. This is a classical problem in dynamics. It's been studied for centuries. We're just attacking it from a different angle of program analysis. But what really drove us to this problem was a motivation in invariant generation. So last year we presented a technique that is able to compute linear models for arbitrary loops. And if I can compute summaries for these linear loops, then I can translate those into invariants for the original loop. So this is really about practical invariant generation at the end of the day. And to give you a feeling for what this looks like, let's consider, as an example, binary search. Right, so binary search has memory, it has conditionals. The body is not a linear transformation. But this linear transformation does capture some interesting features about its dynamics. So the way that it captures them is encapsulated by this simulation relation. So we say that a state of the original program is simulated by a state of the linear loop. Exactly when this x variable is equal to the tix variable, the y dimension is an upper bound on the difference between high and low, and the z dimension is exactly 1. Right, this is a simulation relation, which means that for every step that we make in binary search, there's a corresponding step in the linear loop, and as a result, I can take this closed form representation of the linear loop's behavior and translate it back into an invariant for the loop. So in particular, this allows me to analyze the exponential behavior in the linear loop, this exponential decrease in the y dimension, to prove a logarithmic bound on the running time of this computation. So this gives us a nice principled way to generate nonlinear invariants for real code. All right, so hopefully I've convinced you that the problem is interesting. Now I'd like to convince you the problem hasn't already been solved. So as I said earlier, this has been studied for a long time. Surely mathematicians must have some answer to how to deal with iterated linear maps. And so the mathematician's answer is symbolic matrix exponentiation. So given a matrix A, I can compute A to the k symbolically, which is to say I can compute a matrix whose entries are expressions. And they're expressions of a particular form, which we call exponential polynomials. So these are sums of products of algebraic coefficients times some exponential terms times some monomial. So this, so generally speaking, the way that we compute this exponential is just by computing the Jordan normal form, and this immediately gives us a method for summarizing loops. Right, so if I have the linear loop x gets ax, then we just summarize it by there exists some natural number k such that x prime is equal to a to the k times x. This is a closed form representation of this loop. So this kind of solves the problem, but in another way it doesn't, because these closed forms are very difficult to reason about. So in particular, asking whether one of these exponential polynomials with over the algebraic numbers has a 0 in the natural numbers, which is like saying, can one of these matrix entries ever be 0, is equivalent to Skolom's problem. So this isn't known to be undecidable, but isn't known to be decidable either. So this problem has been open for 80 years. We don't know whether we can actually find roots. So the essential problem isn't really the nonlinearity of these systems, it's really algebraic numbers. So when you exponentiate algebraic numbers, you get all kinds of weird cyclic behaviors that are difficult to reason about. So that brings us to the starting point of our work, which is how do we avoid algebraic numbers? So the contributions of this paper, and essentially just the outline of the talk as well, is as follows. So first I'm going to talk about or give a characterization for when we can express a closed form representation for a linear loop using just the rational numbers, and give a polytime procedure for computing that closed form. Then I'm going to show that if we have a linear loop that doesn't satisfy this condition, then we can always approximate it by one that does. And then finally, I'll show that the fragment, or this logical fragment we use to express closed forms for linear loops is decidable. All right, so let's start with the known cases for summarizing linear loops. The first case is that if the eigenvalues of this matrix are rational, then the exponential can be expressed just using rational numbers, right? The exponents are always in terms of the eigenvalues of the matrix. A second case, which is less commonly known, is due to Bourgeois, which is that if A generates a finite monoid, which is to say that it has finitely many distinct powers, then its exponential can be expressed in Pressburg arithmetic, which is an even weaker theory. So we'd like a common generalization, and what we arrive at is the notion of periodic rational matrices. So we say a matrix A is periodic rational if there's some power p such that a to the p has all rational eigenvalues. And the least such p we'll call the period of the matrix. So it's not too difficult to see that if a matrix is periodic rational, then we can express its closed form just using rational numbers. And the basic idea is that I'm going to take this a to the k term, which is normally expressed using algebraic numbers, and I'm going to write it instead as a to the p to the k over p times some remainder term a to the I. So this is just the remainder of k over p, or of k after division by p. Right? So I just then need to do a k split over all possible remainders, and I'm done. Right, so the reason this works is that a to the p has all rational eigenvalues, and by the first point, I can express this exponential just over the rationals. All right, so the problem with this naive solution is that it's exponential space. So the problem is that the period can be exponential in the size of the matrix. So that's not great. And our solution to this problem is a device we call the periodic rational spectral decomposition of the matrix, or PRSD. So the PRSD is a set of triples, which basically just identifies all of the eigenvectors, all the eigenvalues, and also sort of the periods, the component periods of the matrix. So a set of triples such that for each I, Vi is a generalized eigenvector of a to the power pi with eigenvalue lambda We want all of these vectors to be linearly independent, and we also want the vectors to be maximal in a sense that I'm not going to describe any further, at least in this talk. So the way that the PRSD solves this problem that a to the k takes exponential space is that if we multiply this equation on the left by any of these vectors, vi, then we get an equation that we can actually compute in polytime. Right? The intuition being that each of these vectors is sort of exhibits periodicity at a lower period than the matrix itself. The matrix has a period which is the least common multiple of the periods of all of its components. So I'm just like separating it into a bunch of different components. So I can think of each one of these equations as being, or each one of these vectors as being sort of a projection on a single-dimensional space that is easy to compute because it has a low period. So a matrix is periodic rational exactly when its state space can be recovered from all of these projections, which means that I can rewrite this equation that takes exponential space using this equation that takes polynomial space just by taking the conjunction over all projections. So yeah, this is it. This is a polytime computable closed form representation for matrices that satisfy this condition. All right, so now what happens if we encounter a loop in which there are eigenvalues that are not periodic rational? We don't want our analyzer to just give up. We would like to compute some information about the program. And it turns out the PRSD is a solution to this problem as well. What I'm going to do is collect all of the vectors in the PRSD into a matrix, and then I'm going to perform this factorization. So I'm going to find the unique matrix B, which is always guaranteed to exist, such that VA is equal to BV. And this matrix B is always going to be periodic rational. It's going to satisfy this condition. So this equation here can be written in more familiar style in programming languages, like this. This is one of these commuting diagrams. We see that what the situation is that this A is a transition system, as well as this B, and V is just a simulation relation, saying that every step of the A linear loop is matched by a corresponding step in the B linear loop. So just as before, we can translate invariance from B into invariance for A. And moreover, this is the best way of doing this. There's no better periodic rational approximation of A in a sense that we can make precise in the paper. All right, so the overall pipeline for generating invariance for programs is that we'll start with some general loop. We'll apply this this technique from last year to model it as a linear loop. Then we'll apply these techniques to abstract it by a periodic rational linear loop. We'll compute closed forms for that loop, translate those back into being invariants for the original program. All right, so this is a complete picture that allows us to generate nonlinear invariants for real programs. All right, the last thing I want to talk about is reasoning about this logical fragment we use to express closed forms. So there's two key steps in the decision procedure for this logical fragment. The first is to eliminate all of the symbols except for the loop counter. So these are all the symbols that correspond to program variables. So the intuition here is that although the formula contains nonlinear terms, the way that the nonlinearity appears is very constrained. Nonlinearity is sort of essentially due to dependence on the loop counter, not on the program variables. And what this means, more concretely, is that I can think of all the terms in my logic as being linear, but where the coefficients, rather than being numbers, are exponential polynomial functions. And as a result of that, I can apply essentially linear quantifier elimination techniques to get rid of all of the variables except for the loop counter k. So after this variable elimination procedure, we're left with a residual formula that only involves one variable k. And then we're just going to find an upper bound for how high k needs to be. Right, k is a natural number, so I can just check I'm computing some sort of small model property for this logic. So the idea behind why it should be possible to compute such a bound is that exponential polynomials over the rationals are always eventually dominated by a single term. So for example, I can look at this exponential polynomial term right here and syntactically determine that it's eventually going to become negative and stay negative forever because the term with the highest exponential and greatest monomial has a negative sign, right? So that's all there is to it. So finding, I guess exponential polynomials have this sort of transient period where they wobble around for a bit, but then they stay either positive or negative forever. So then this is just a matter of finding the length of that transient period, which is just sort of a bit of calculus. So the consequences of this being decidable, first of all, we can check whether quadruples are valid involving linear loops with periodic rational eigenvalues. And second, we can check termination starting from some initial condition. All right, so the last thing I want to do is just give you a couple experimental results. So we ran this technique, which we're calling PRSD, on a suite of 101 small benchmarks collected from a variety of sources. This graph plots running time on the y-axis and the number of assertions we were able to prove correct on the x-axis. So we can see that PRSD is able to prove more assertions than any other tool and is significantly faster than software model checkers that appeared before it. So the difference between PRSD and the previous technique that we presented last year is not so great, but maybe an interesting result is that we have a better theoretical understanding of what the PRSD is doing than we do of last year's technique, which was based on replacing these algebraic numbers essentially by uninterpreted function symbols. Okay, so summing up, the contributions of the paper is one, a characterization of when we can express the closed form for a linear loop over the rationals and a polynomial time procedure for computing it. We showed that every matrix has a best approximation as a periodic rational matrix, and that this fragment we use to express closed forms is decidable. And that's it. Thanks.
Please come up if you have any questions. Come up to the front because there's only one mic. There's one question, provocative question online. It says, what would happen if you apply your technique to famous open problems like the Collatz conjecture or other similar problems?
So for the Collatz conjecture in particular, nothing good would come out of that. So this linear transformation, or this linear loop is, sorry, we can always approximate an arbitrary loop by a linear loop, but it might give us a trivial approximation. We might essentially just return top. So in the case of the Collatz conjecture, there's no dimension that's actually decreasing, or no dimension is actually being transformed by a linear transformation that's common to all branches, and as a result, we'll end up with a zero-dimensional approximation, and we'll get no information out of the loop. Yeah, so there's no guarantees on the quality of the approximation, just that it exists.
So the answer, it will disprove the conjecture. All right. Any other questions? Yeah? All right. I have a practical question in terms of linear loops and other numerical loops. Like, I mean, most programs are not just numerical. So how applicable is this? I mean, like, how would you use it on a bigger program with heaps and data structures and so on?
So yeah, right. I mean, it certainly applies. You wouldn't compute any information about the heap unless you somehow sort of lowered it into variables. So yeah, it's an interesting question of how you can combine this with shape analysis, but this is really just a numerical analysis. We won't compute any information about the shape of the heat.
And one more question online. Can you use this for improved parallelization of sequential loops?
Let's see. So I guess you could imagine that like data dependence testing that's used in parallelization uses sort of similar looking techniques. So you could imagine that maybe that would be a possible application point. I certainly haven't tried. It might be an interesting direction.
Cool. One last question and then we'll wrap it up.
So what if in the while loop you have the branches? I mean, like if else, if I have you have to maybe to affine transformations. How do you summarize the
how would we summarize a branch like in?
Yeah. Yes, actually you have this if else loops here, right? If else branches here. Yes. How do you summarize this if else branches actually?
Yeah. So what happens in this particular example is that we're going to find that we won't be able to compute precise information about low or high because neither is updated predictably, but the difference between high minus low is updated predictably. So we're going to lose information about the program, but we won't lose all the information about the program. So we'll still be able to find a bound on the decrease of the sum, or the decrease of the difference between high and low.
Okay.
So yeah, we'll lose information. It's just like a join in standard and abstract interpretation. We're going to lose information. Hopefully we don't lose everything.
Okay, thanks.
All right. Thank you, Zach.